Welcome to CMP 302. We're going to do some benchmarking of GCE on this. Well, GCP, but mostly GCE instances. This session is Dory enabled. Please save your questions for the end, and please use the Dory, and it'll be moderated after the session. So what's in store for you? We'll be talking first about PerfKit Benchmarker. PerfKit Benchmarker is an open source project at Google where we're trying to make a set of tools to make benchmarking easy for everyone trying to figure out which cloud provider to use. Then we're going to go over a slew of benchmarks, probably too many data slides. I don't know how I got them approved, but there's a vast number of slides that will show IaaS benchmarks in many ways. Then last week, we announced the C2. It's a new instance type at Google, or at GCE. And I'll be comparing that to our older N1 instances, and we'll see if performance is better or if it's different on the C2 versus the N1. Spoilers, slightly better. And then I'll be giving you a couple demos and some scripts to take home that are pretty easy to use if you want to compare and contrast different instances, almost anything. You want to slice and dice IaaS pretty easily. Okay, what is PKB? Like I said, it's an open source set of tools that we've created to try and make it easy to compare the performance of various components of the cloud platforms. It supports most cloud providers. It has on the order of 50 different tests that you can run to try and get performance data on the different providers or the different services. I think it's particularly good at getting IaaS. We started working with GCE pretty early on this project, and we think we hit most of the major touch points that people are interested in with respect to performance for GCE. We also have a number of tests for ML, which are being added constantly. I've put more resources over time into our ML tests. They test all the different configurations, be it GPU, TPU, or just running on the processor itself. We also do database tests. The database testing is a big art, and we are continually expanding our set of tests for databases, but it's not complete at this point. It's just a vast amount of work to get them all complete, but we're working on it. And then we have some big data tests. So some tests that hit BigQuery, Dataproc, Dataflow, and a bunch of other services, and compare and contrast them. But these services are a little bit bespoke sometimes, so comparing them can be a little bit difficult, but we give it a shot. And please try it and tell us what you think. Some random stats about PKB. It's a moderately successful project. We have a little bit over 300 forks. We have 1.5K watch forks. We get on the order of 3.7K commits, so 4,000 commits, and about 100 contributors across a number of companies. What I really get a kick out of, though, is quite often when I see an industry report come out from one of the big vendors, and I look at the addendum or the appendix, and I can see how they did it. It's pretty common now that I'm seeing PKB referenced and used as scripts to generate their reports, it's starting to get more and more use for benchmarking, especially, like I said, IaaS. IaaS being infrastructure as a service, so VMs, networking, disk, and we'll go over those. So why do you want to benchmark the cloud? Well, performance is usually one of the three top metrics that people use when trying to decide what cloud to go to. Security, obviously top of mind. It's been in every keynote. Very, very important. Reliability, availability, very much top of mind. Benchmarking that is moderately difficult. We'll talk about that near the end. But that's also top of mind. But performance, or price performance, quite commonly, is right up there in purchase decisions. So it's moderately important. The best way to get performance data is by doing POCs, of course. So you take all of your apps, you somehow come up with some model where you can bundle the good percentage of them up, the crucial parts that you believe, you move them up to the cloud, and you run that. The problem with POCs is that they're quite expensive, and they're just complicated / expensive. So they're the best, but expensive. Is there something you can do beforehand, maybe kick the tires, that's cheaper? Yes. Especially, like I said, IaaS, the models are pretty simple for figuring out how IaaS works. IaaS is unbelievably complicated underneath the hood, but from a user's perspective, when you think about the performance characteristics, it's not overly complicated. So we can come up with a bunch of tests that allow people to compare. And we'll see a bunch of this. And it's moderately easy and inexpensive. So we're going to be hitting 5 main metrics on IAS. Boot time. It's a weird one. I know at first you're going to wonder why boot time. I'll go into why boot time is important. After that, we'll talk about compute. VMs are the dominant expense for almost every person who uses cloud. And what do you do on VMs? Generally compute. That's probably, in many ways, the most important metric. Memory, a little bit of a fringe metric, but it can show you sometimes some interesting characteristics. And again, incredibly easy to run and moderately easy to interpret, so might as well kick the tires. Networking, the VMs are in the cloud. Networking, sending bytes, receiving bytes is what they do. Incredibly important. Depending upon the app, could be crucial. Many compute apps are actually latency bound. And if you do a lot of HPC in the cloud, there's a number of reasons why networking is important. Serving, so incredibly important and actually shockingly complex. From our perspective, again, we're just going to do performance, but there's so many ways to slice it, as we'll see as I just inundate you with slides and data, that there's a lot to compare when it comes to networking. And finally, remote block devices or disks. You need to boot your machines. You got to fetch data from somewhere. It's either from usually cloud storage or from your block device. Pretty important in some scenarios, especially databases, where databases hammer the remote block device incredibly hard. And knowing how the block device responds under this kind of hammering for databases especially, but all kinds of solutions, be it NoSQL databases or traditional databases, remote disks can be right front and center with respect to how your overall lab performs. So benchmarking your remote disks is pretty important. All right, boot times. Like I said, kind of a weird one to start with. You'd think compute. So why boot times? Well, the first thing is that they're the customer's first experience when they get onto the cloud. I have a really quick story about this that I find funny. A friend of mine has an ML startup. He's doing moderately well. He's on some cloud provider, and another cloud provider came in and gave him sufficient credits to run all of his apps for 2 years. So he was, as CEO and the guy who's responsible for the finances, he was totally bought in. And he told his devs, we're moving to this other cloud. The other cloud had not the best boot times, in particular, actually. There were a number of other issues, but boot times really irritated the devs. It irritated them so much that somehow, and I still don't know how this is possible, they rebelled against the CEO, and they stayed with their other provider where they were paying money. To this day, both he and I are incredibly confused how this all played out, but it's an amazing story as to why boot times are moderately important. As VM lifetimes shorten, just rationally, as VM lifetimes shorten, the boot time becomes more and more important. And I'm going to show some data, both how internally, when we view all of your workloads, how long you keep machines up, and then we'll show how internally for us, how long we keep machines up, and then aspirationally where we think we should go on that. And finally, it really does show, boot times show technical excellence. They hit the whole stack. You hit the top of the control plane, you hit the job scheduling, you hit network programming, which is crazy complicated, PD programming, and you hit the actual data plane to get the bytes onto the machine and the machine to get booted. And if you can drive that time down, it just shows technical excellence throughout the entire stack. I think it's a really important metric. So then I'll show you some crazy graphs of where our boot times are today. And then I'll show you if you can measure this yourself, assuming my laptop keeps powered. Lifespan of VMs. So today, this is what you guys do in our cloud today. This is a CDF. I should tell you, actually, this is my favorite. You're going to see way too many CDFs today. A CDF shows at a given percentile what the value of interest is. So in this case, on the vertical axis, it shows you the percentile, be it 0 to 1, 100%. And along the horizontal axis, that is hours of duration of the VM. You can see it has a pretty sharp slope. And at your P50, for all of your workloads, is 12 minutes. That is the median time of a VM's life today in GCE. Pretty short, you would think. And it is pretty short. And you're doing it Not wrong at all. I think you're doing it exactly right. The entire idea behind moving to cloud is that it's incredibly responsive and agile. And you can just use compute the second you need it, and then you discard it, and it doesn't cost you anything after that. This is the exact right way to use it, and you're using it right. And this is what we do in Google internally. In Google internally, we're doing the same thing you are, and that's when we need compute, we spin a container up for us, but we spin up a container, and then as soon as that compute's necessary, we throw it away so someone else can use it. And we're down to 6 minutes here. And we actually think that aspirationally in GCE, we should drive this time down even more. We think aspirationally that VMs should be thought of like threads, and that you should be able to spin up a VM in a sub-second, that's the whole stack, and then you should be throw it away as soon as you don't need it. We think this is the future, we're driving towards it, but like I said, this is a full stack problem and it's moderately hard. Here's why it's a full stack problem and it's moderately hard. This is from our internal monitoring. This shows at a high level, each one of these lines shows like a large section of code that is responsible during a VM bring up. And if I click on this in our internal monitoring, these expand infinitely into even more subsections that are broken down. But this is the high level view. And what contributes to boot times? It's of course the control plane. The control plane itself is incredibly complicated. It has to do a ton of business logic. It has to then do a really weird number of quota management. It is strange how many different quotas are modified in the construction of a VM. Then that is sent off to the actual job scheduler. Whoa, I'm on my demo. A little early, sorry. Then it goes on to the job scheduler. And the job scheduler will find a physical place for that VM. We have, as you know, custom VM types. This makes it so we have a bin packing problem to solve globally for the cluster. Every time you schedule a VM, we batch it up a little bit to make it so it isn't terribly compute intensive. But yeah, so we have to find a physical place for it. Then once it finds the node, a lot of containers and C groups have to be set up. There's a lot of computation that has to happen on the node to get it ready. Then in the background, we start programming the incredibly complicated virtual networking while we get the bits onto the machine as quickly as possible and we program the remote disk, and we get the bits onto the machine to boot the OS and run through that. And then there's a little bit of overhead for SSH while we play around with keys to make it easy for everyone. But anyway, the total sum is on the order of 20 seconds as a P50. But is there a distribution? Yes. Yes, there's a distribution. These are our 4 main geographies. I'll talk about that in a second. You have EU, you have the US, and you have Asia on here. Each one on a series, on a CDF. Again, the CDF percentile, vertical, number in question, in this case, seconds to boot on the horizontal. And as you can see, the P50, if you have your glasses on, because it's really small, the P50 is on the order of 20 seconds for both EU and Asia. And it's a little bit more, maybe 23 for US. US is where it curves a little bit. That's due to our US zones being quite a bit larger, and there's a constant struggle between the people making optimizations throughout that stack and the problems they get as these cells get larger and larger. So there's a constant struggle. This CDF moves back and forth continually as the poor devs struggle mightily. There is one more. You'll see there's 4 lines. This is an in-house joke, I am sure, where my staff puts Canada as one of the top geos because I'm Canadian, I am positive, and they continually do this to me. All right, let's try a demo. Pretty quick, hopefully. Ooh. Let's do what? All right. So what this is doing is this is running PKB. We're launching on the order of 20 VMs simultaneously out there into the cloud. These are N1 standard 4s. And wait, I'll get the results page here. This is from the previous result. It'll hopefully change as PKB does its thing. So we're going to fan out 20 machines, only 20. You could do hundreds, up to you. But in this case, we're going to do 20 machines. We'll record the times. Some script will run to create a CDF out of this, and we will see the CDF within 3 minutes approximately. So, and most of that time is spent cleanup. There's like 1.5 minutes to send out all the machines and to gather all the data. And then right now it is app get updating. Oh, it's finished. It's generating the graphic this time, and now it's going to tear down. We should have made the tear down asynchronous and hidden, but this is what happens when we make demos. So we're gonna span out 20 machines and see if this meets the previous internal metrics that we have for how fast our boot time is, and hopefully it should finish tearing down momentarily. Like I said, PKB is a moderately large project that allows us. This is a pretty easy script to run. The graphics, if you're really good at R, it's easy to make the graphics. That's probably the hardest part of this. There are a number of graphing solutions if you want to use that. In this case, like I said, I want to do all self-contained, so we used R. So anyway, oh, of course it's already done. So if I reload this, oh God. All right, that didn't work out. Let's go here. There should be a link that will be updated. Oh my. There you go. So this is the current CDF. This is the CDF we just generated of boot times. You'll see at P50. Amazingly, it was at 15 seconds. That's pretty good for us. This is running Debian 9, which is our best OS. Of course, boot time varies on an OS basis, but this is our best. All right, back to the slides. All righty. So compute. Well, this is what you do with VMs generally, so incredibly important. Varies on a couple dimensions, varies on SKU. We're going to try N1 versus C2, see if the C2 is any better. There's also single-threaded versus multi-threaded. This corresponds to Specint speed versus Specint rate. Specint rate is almost certainly, in almost all cases, much more important, but there are a few fringe cases where Specint speed is more important. Also, the C2 is even better at C2 at single-threaded, so I'm going to bring it up, of course. I'm trying to sell my C2s. And then we're going to talk about, can we do this easier? We can run Specint. It's the granddaddy. It's the best. It's the best metric overall for doing compute, but it takes a while. It's moderately expensive to run. Can we get something like Specint results with some other tool set? And we'll see if that's possible. And then we'll see if we can measure it ourselves. I'm not sure I'm going to run a demo, though. So it's a little bit faint, sadly. I don't know if you can all see the light green. There's two lines here on the CDF. There is the light green, which is the N1, and there is the dark green, which is the C2. The C2 Specint speed, the single-threaded performance, is in this metric on 8-core VMs. Again, this is not perfect because we are in a zone by ourselves, and while the N1s are living with a lot of other people or other customers, so they're slightly disadvantaged. We don't know if this result will hold once we get to prod. But right now, on single-threaded performance, we're seeing up to 60% difference between the N1 and the C2, which is pretty impressive. You'll note the CDF for the C2 actually has a little tail at the bottom there. That's not perfect. It should be perfectly vertical. We think what happened here is that I asked for a lot of samples from my staff when we cranked it up to 10 in the little tiny zone we had because it's pre-release. And we think we were making multiple versions of Specint hit the same socket. And Specint at 8 cores pretty much saturates the memory bandwidth of a socket. So when you get multiple, they will interfere with each other. It's a known issue with Specint and normal CPUs. You run out of memory bandwidth. It's moderately hungry. So that's 60%. Let's see what Specint rate. Specint rate is, like I said, much more important than Specint speed for most uses. Specint rate is multi-threaded. What is the throughput of your VM? These are N1 standard 8s. The CDF, again, there's two lines. I don't know if you can see it all the way in the back. One all the way to the right, one closer to the left. Again, CDF with percentiles and numbering question at the bottom. And the C2 is doing great. On this case, with N1 standard 8s or C2 standard 8s, we're seeing up to 50% difference at P50. During our press release, we said 40%, which is very safe, we think. We are pretty safe to say that most of the time you will get 40%, at least 40% more performance with a C2 on a per core basis than you will with an N1 rather. So it's a pretty big jump for us. I guess I should give a little bit of data dump on the C2 itself. It's a Cascade Lake processor running with, I don't know if I should say exactly how many cores, but substantially less than we did inside of the N1. So therefore, when you go to MCC versus XCC with Intel or with anybody, having less cores on a per chip means you have way more TDP per core, and you will get far higher clock rates, and we do. Furthermore, we did a few other things. The software is slightly different in the C2, and the memory is clocked slightly higher in the C2 than it was in the N1. And the overall effect is a tremendous improvement in performance on a per-core basis. All right, so Specint. Like I said, Specint is the granddaddy. I'm not going to fight Specint. It's like 100 PhDs worked on this for 20 years to come up with some random set of benchmarks with some weighting, and that is the best. Still the gold standard. I will always run it. But is there anything we can do that could perhaps be a little bit cheaper than Specint? Furthermore, Specint takes like a couple hours to run, 2, 4, sometimes 24 hours to run, depending upon VM size. And I got plane to catch. I can't wait for 24 hours. I can't do that with you right here. We could fork all the tests, obviously. Specint is, as you know, comprised of on the order of 20 tests, 20 to 30 tests. We can fork them all individually, bring them all back in, geomean those, and get a number back out. But even then, it takes quite a while to run. So what about this? Why don't we try running StressNG? It's a package out there which has a variety, maybe 50 different tests internally. Geomean all of those together and see what the result is. It turns out it's pretty correlated with Specint. There'll be in the GitHub, we'll give an approximate correlation coefficient to see how good StressNG is, but it's pretty cheap. Then we'll take a look at that. All right, so let's see if we can do that. Let's go to the demo, but I don't think I'm going to make you go all the way through a running of it. Oh dear. And here we go. This is what the end result is. I could have hit the button. If we have time at the end, I'll hit the button for everyone, and we can see the lines slightly change from left to right. But we got about 55% difference in performance between the C2, or is it 45 in this case, between the C2 and the N1, which is within our bounds at P50. And the CDF looks beautiful. I love the straight vertical CDF. That's what you want to see in a CDF, incredible consistency. And you're getting a little more consistency on the C2 that we're running on right away than we do on the N1s. And again, that's almost certainly due to a couple of factors. A little bit different software in the C2 as compared to the N1, so we believe that is going to improve our performance or consistency. And using smaller core counts on a given socket means you have less probability of having a neighbor. So it's pretty great. Back to the slides. Alrighty. Let's do it live. We'll do it live. Like I said, I'll do it live at the end if we have time. It takes 3 minutes or so. Alrighty, memory. There's a bunch of great memory tests. You know, anyone who's investigated this finds like a bajillion of them. Multi-chase, LM-bench is great. Stream is part of HPCC and is one of the granddaddies of memory performance tests. And there's just a vast array of these. We'll be using multi-chase here because developed at Google, and I have to give my friends props. So we'll try multi-chase. It's generally not as useful as spec or compute, but it can show a few issues. It can show the NUMA support of the VMs. Is it perfect or not? Or are there NUMA issues underlying? It can tell if if you look at the graphs correctly and you squint and you turn your head, you can figure out if there's host huge page or giant or large page support. Like 1 gig or 2 meg pages. If you really look, you can probably figure this out. And so you can also figure out if there's some weird kernel, KVM, host memory manager issues where locking comes into play. Because once in a while, when you do a memory benchmark, you can see some interesting effect, and you can figure out if way underneath the hood, there is some kind of kernel locking bug that is causing you issues. We've got a lot of mileage out of running these tests over the years, and we found a number of bugs throughout our stack and perhaps in others. Again, a little bit faint. I have minimal control in my staff. This is the dark green is the C2. The light green is the N1. And this is latency of multi-chase. So those are in nanoseconds along the horizontal. Vertical, of course, is always in a CDF, is percentile. What can I say other than an enormous improvement? We are talking about big numbers. The P50 was about 142 nanoseconds with the N1, and with the C2 we're talking about 87 nanoseconds, which just is about speed of light given how virtualization works today, at least. And the real improvement is at the tail. That we had some real tail issues with the N1 on memory benchmarks. This was weirdly, the tails were not due to memory itself. They were due to, interestingly, threads. So what would happen is you have a vCPU thread, which is what backs what you think of as a CPU within your VM. And once in a while, because it's really at the 99 point something up here, it's really far up, a user space thread or a kernel thread would preempt you. And this particular benchmark is very sensitive, and it would detect that and would think that was an incredibly long memory latency fetch, more precisely, while instead it was just a context switch underneath the hood. So with the software, with the C2, we have been pretty rigorous in making sure, number one, every user space thread cannot interfere with a vCPU thread, because there were some that were interfering periodically. And furthermore, we have been working diligently to move every possible kernel thread out of the way and sequester them away from vCPUs. That's an ongoing battle. There will always be a couple kernel threads that can mess you up at the P99 point. I'm gonna have to get this right. 99999 is where we're shooting for. So it's we're going to 7 nines there. There will always be a couple kernel threads that can mess you up unless you do drastic changes, but we think we have line of sight to 7 nines. We're not there yet, but we're pretty close. So anyway, that saying, and the other part of the curve here where we had problems in the N1, as you can see, it's slanted pretty early, not just the extreme tails, was NUMA support. We didn't have good NUMA support with the N1. With the N2, the NUMA support is perfect, not too hard. We did it right this time, and it's perfect. So if memory latency is crucial to your app, likely you will be buying a C2. Demo, let's do it live. I'm just going to show the graph again because taking 3 minutes probably is not right. Right on. So if I just run this again at the end, if I have an extra couple minutes, we'll run these. And you can see that this is exactly the same as the graph we just ran. Interestingly, I should tell you about how much these cost to run. Like I said, I've been telling you before, it's cheap to run these tests. These tests take on the order of 3 to 4 minutes. This is done with 20 VMs times 2, so 20 C2s, 20 N1s. A C2 or an N1 takes costs at the smaller sizes, about 10 cents each. They're running for on the order of 1/20th of an hour, so that's 10 cents per hour. Multiplied by 40 VMs, that costs you 20 cents. So it's not overly expensive to generate this graph. You could even, if you want, get a little more fidelity by cranking up the number of instances if you want the nice smooth graphs we had earlier to 100 or 200, and it's going to cost you $1. So these aren't horribly hard to create on your own. And it's probably a good investment. Back. All right. Networking. Oh, we're blowing through the slides. I might have time to run a demo if I have power. All right. There are a vast array of networking tests. There's TTCP, and it has a really long set of descendants that have forked and branched and slightly changed to TTCP. There's iPerf. Everyone's used iPerf. It's pretty much a classic, and it gives very simple results. And there's NetPerf. NetPerf is complicated, but the author is pretty cognizant of just about everything going on with networking. This is why it has on the order of 1,000 switches. And he works at Google. He's a friend of mine. So I'm going to use NetPerf in the following examples. But it's a great test. It's just a little difficult to run considering the number of flags. Again, PKB will hide all the flags for you and just output a bunch of samples that you can throw through some R scripts or whatever your favorite visualizer is. 15 minutes left on my laptop. And you can then see a CDF. So the networking is super complicated. These are snags, I call them, but just complications. There's internal versus external IPs, very different performance characteristics because the routing is completely different. There's rate limiters. Some clouds have rate limiters on their networking, and that completely changes everything about how you measure networking if you want to see where their rate limiters work or they kick in. Distance. We'll be going with distance matters both at the short scale within a data center. So if you can do placement of machines next to each other, that actually saves you a little bit of time because of the switches involved, not due to speed of light. But also distance matters then for how far your data centers are far from each other, because that will impact replication speed. And of course, speed of light matters in fiber, matters a lot for when you go across continents. Oh, and I went back a second here. I forgot, fabrics vary. We have built over GCE over the last 5 years. Over the 5 years, we have revved our fabrics time and time again. Some of our older zones have older fabrics, which we then rev, but it takes time. So fabrics vary, and that makes TCP times or latencies vary dramatically. And finally, utilization. Utilization varies on a per zone basis because zones are big and or small, and just for some reason, VMs in some areas are much more heavily utilized than others in terms of networking, and so you get a slightly more noisy neighbor effect. All right, what does this all look like with all those caveats? This is our intrazone networking. As you can see, this is a one line per zone, and there's a good amount of difference, especially the tails of those zones. That's normally due to utilization effects. But there's also differences at the P50, and most of those are caused by utilization and by different fabrics. There's like two, if you squint, maybe you can see two giant bands in the middle there, and that basically represents a couple different generations of network fabric that we use. We are upgrading all of our zones commonly, and the worst ones on here, if I guess I can say it, happen to be in Asia 1. We are upgrading those, and we assume they will move slightly more to the left. And again, sorry, I should have said what kind of graph this is. I hope this is clear by now. It's a CDF, percent to vertical, horizontal, unit of interest, in this case, microseconds. And at P50, I should read the slides. I had notes here. We're talking, this is P50 in most modern zones. At P50, we're talking 50 microseconds, which is pretty reasonable for ping pong latency, or TCP/R, as this test is called. All right, this is going to be really hard to see. I don't know, I might have to walk down there. There's a little red line here if you have your glasses on. I didn't realize how thin this would be. Down here for the C2, it's a little bit faster than everything we have today. This is due to a couple of reasons. I don't know if you can all see that, but it's a little bit over. It's at 38 microseconds as opposed to the rest of our networking. Why is it a little bit faster? A couple reasons. One, obviously, the faster frequency of the processor allows it to really blow through the TCP stack, which is one of the main components of latency when it comes to running TCP/RR. Obviously, if you use MPI and some fantastic MPI library that may or may not be released soon, then that all goes away, and this time reduces dramatically. But with TCP, you need your processor to power through that very complicated TCP receive function that you can go take a look in the kernel. It's hilarious. Anyway, one of the things that this is using placement groups. Placement groups are rather by happenstance. The C2 was in very low quantity when we created all these graphs, and the machines were put very close to each other physically. Normally, our default cluster manager configuration is to spread wide across the entire cell to make it, or zone, sorry, in GC parlance, across the zone to make it so you have higher reliability. So you have your no one failure domain will hit two computers. So this is a little bit better than it probably will be for a computer in real life, but we think it'll be pretty good. We think that we will have a pretty good product here, and this will have pretty solid frequencies, or rather TCP/R latencies. All right, between zones. What can we learn? Like I said, you can just run the script again. There'll be a script for this, and you can generate these very pretty bands. You can see, again, there are two big clumps for how our clusters work, depending upon basically fabric, and we have a policy on distance. So you're talking basically 220 microseconds or 270 microseconds when you're wanting to go between zones in GCE over TCP. It's moderately fast. Those are our largest zones and regions. And then there's the fringe zones that are a little bit faster to the right and a little slower to the left. The little ones that are closer to the right, those are almost always caused by somewhat considerably smaller zones. We have a few zones like the Montreal zone that was on an earlier slide that are very close to each other physically. And so they have incredibly better times. I mean, the times are substantially better for those. And again, going all the way to the left, there are a few zones that have tails, and those are unupgraded zones. As I said, Asia is one of those areas. Speed of light. Very important for many applications is transiting from, this graph is really hard to read, from one geo to another. And this is all of our interconnects between every zone in GCE. And this is almost entirely, it's not that interesting of a slide in that it is almost entirely generated from speed of light and fiber, plus a couple how many hops if you are a little bit inconsistent in your routing. But generally it follows those numbers almost exactly. One interesting thing from this graph is if you can take a look very carefully, it's really hard, about 3/4 of the way up, we see a slight change in the CDFs as you, around 3/4 for a number of the lines. This was caused by a routing glitch we had in early February, or last week of Feb, sorry, and it got caught. You too can run these tests. They're, again, incredibly inexpensive to monitor your cloud and find out if you lost like 6 milliseconds. This is in milliseconds, by the way, for your routing because of a small routing glitch. Wow, my battery's dead. Finally, I think this is the final slide for data, is networking throughput. Networking throughput for GCE is pretty, compared to other clouds or in general, is pretty generous. We give 2 gigabits per second per core, and that is not throttled in some kind of mechanism. So that's a lot of bandwidth to give on a per core basis. This caps out today. I don't remember our docs, but I think I'm safe to say it caps out at 8 cores. So at 16 gigabits is where we cap out. There's a lot of work ongoing to increase that number. And in the subsequent weeks, months, you should be seeing announcements that we have gone considerably higher on a per core basis, or we increased the caps. But this is where we are today. And this is a CDF, yet again. Percentile vertical, horizontal is throughput. And you can see most of the time, you will get on your N1 standard 8s, you will get, and each line is a zone. You will be getting your 16 gigabits a second. Once in a while, it will drop down. Some zones drop down more commonly than others. Again, older fabrics generally is where you'll see more of the issues on the tails. Ooh. Wow. All right. Next. And we can try the demo. Let's see, I'm almost at my last dregs here of power. And two CDFs, the C2 and an N1 standard 4. I don't remember what zone the N1 standard 4 was in. You can see the tails are fantastic on the C2. This is, again, almost certainly an artifact, number one, of the high frequency of the C2, and secondarily of them being in close physical proximity. This is essentially with placement groups. Even though it wasn't a placement group API, it was that they happened to be there because we had very limited quantities at the time. But the numbers are fantastic. 38 microseconds, almost a P99, almost no tails. We hope that we can deliver this relatively soon in large clusters. Back to the slides. Alrighty. Oh, I forgot there's more. Block devices. Remote block devices are just like networking in that they're complicated. They have all networking problems, plus they have media problems. They are very complicated to benchmark correctly. There are many SKUs. Every cloud has a bunch of different SKUs. Every zone is completely different due to fabric being different, due to the generation of the media being different. Cloud is always like this. We're always buying different media as the generations go along, so there's a little bit of inconsistency there. Load. The media almost always, or quite commonly, gets slammed, especially for spinning Rust, but even SSD gets slammed continually for these remote block devices. So they're all very highly subbed. And so this causes variance in many different ways. And this all varies on a zone, region, even time basis. So benchmarking this is moderately hard. Drive sizes modify the performance you'll see in many complex ways that are not easily intuited. Number one, obviously, we tell you on the web page, you'll get this many IOPS per gigabyte, and everyone else has a very similar model. But furthermore, it turns out that the internal programming of these things means that larger disks have a little bit more compute necessary to figure out where to do the LBA to PBA translations. And that little bit more compute makes it so that they're just a little bit slower, so you have to try different drive sizes, and they all have different characteristics, so it's just really hard. And throttling. The throttling, because every cloud has block devices that are subbed very hard. They're very hard. They're subbed to a very high degree. They have very complex throttling mechanisms. So you have to understand the throttling mechanisms that every cloud has before you benchmark them. So anyway, that's all this to say, block devices sadly are pretty complicated. But we can just try random reads because random reads are easy. So let's make a device that's on this size, 500 gigabytes in size, throw some random reads against it and see what happens. This is pretty easy. And it turns out for us, the bands are pretty tight, actually. They're on the order of 600 microseconds. And interestingly, you wouldn't know this from external, but I can just say that's about half and half in terms of infrastructure time, in terms of networking and media. And about half of that is compute. There is like I was saying, the computation to figure out where to store the blocks and how to encode them is moderately complicated. And this is pretty common across all the clouds, that computation is actually a large portion of the expense. And you'll see numbers around 600 or slightly around there for most clouds for 4K random reads, the standard. Random writes, a little more random in terms of performance. You have a couple of zones that are obviously where, in this case, the media is quite subbed. And so these are SSD again, where they are pushing the media hard, and the media is a little bit older generation. But the vast majority is on the order of 450 microseconds. You may be wondering, how is a write faster than a read? Because I know how SSDs work. Writes are incredibly hard. It's because, just like most drives, everyone has a little bit of a cheat. We have battery-backed computers that back all of our SSDs. So we triple write to 3 computers that are battery-backed. And I was told by the storage ATL that I have to say battery-backed at least 3 times. We are battery-backed, and it goes to 3 machines. And then when quorum is achieved, then we let you continue. And then asynchronously, it is flushed to the media. In summary, that was a lot of data slides. I'm sorry, but this is what they pay me for. Sorry I put you through that. Cloud is dynamic, and boot times are really what power that dynamism. Please take advantage of quick boot times. Use your computers only when you need them, and turn them off. You'll save lots of money, and everyone wins, and you'll push us harder and harder to be better, and I like that. IIS is complex, but to a first order, you can benchmark this pretty easily and pretty cheaply. All of those graphs, like our graphs, the ones I had that were in light green, have more sample points, but they cost at most $100. And I probably went too crazy on some of those graphs. You can make cheaper graphs for a couple bucks, and you can get a good idea of what's going on. The C2, we're pretty happy with it. So far in all of our testing, we think this will be a fine machine. Please go buy them and make my capacity planners really upset. They don't know how they're going to buy enough so quickly, and I hope you all go out and rush out and buy the C2. It's fantastic. And most importantly, don't trust me. Don't trust anything you saw here. These will be easy to run. Go to that location. There'll be a directory with demos in it really soon. I have people working on finishing the code and getting it through code review right now. So within a few days, there should be a place there, and you can just press up arrow like I did and get numbers and maybe believe them. Thank you.